awards in the field, the most notable of which in 2015, he was elected to the United States National Academy of Engineering for his outstanding contributions to understanding natural processes affecting flow and transport properties of fractured rocks. With that, I will hand over the floor to Professor Elsworth. Professor Elsworth, please take the floor.
Jenna, thanks very much for that introduction. That's frightening. I don't usually circulate my resume, so it's quite restricted. So actually, you seem to know more about me than my wife, so it's quite frightening in itself. But so thank you for the very nice introduction. It's a pleasure to be here. As I was saying earlier in our conversation, one of the silver linings, I guess, from COVID, if there is any silver lining, is the ability to do these things online with Zoom. Is all of a sudden the world has become much more open to transport across boundaries without transnational travel, which is kind of interesting. So today I'd like to talk about some of the stuff that we've been working on in terms of induced seismicity applied to problems in the subsurface and subsurface science. Of course, if you're watching this and you're a geophysicist or a geological engineer, we're the new saviors of the planet. Of course, we all know about the currently highlighted problems of global climate change and how those have come to the fore really severely in recent years and months. And of course, we all know these dire predicted outcomes and what they can be, but the solution to them is not so clear. The solution is to stop producing carbon-intensive energy, but how to do that and how to do it economically is not clear. Some of the baseload power sources for this would, of course, include things like fuel switching to natural gas, carbon capture and sequestration, and of course, deep geothermal power. And these methods of baseload production are haunted to some degree by some technical difficulties, two of which would be the propensity to produce induced seismicity, which can terminate some of these projects. And secondly, the potential that you can't actually realize the things you'd like to do. And specifically for deep geothermal energy, which is an abundant source of power, creating a reservoir in nano, not so much nano, but micro Darcy permeability is a difficult problem to overcome. And so you need to create some disturbance in the subsurface to create some seismicity that goes with that. And of course, the projected problem might be that you produce seismicity, trigger seismicity, which might terminate the project. And so that's kind of the background to what I'd like to talk about today. We've mentioned these different methods for recovering baseload power. And the problems of them are similar in some respects, but diametrically opposed in others. They all require us to do something in the subsurface. But for sequestration, we're interested in not changing permeability. And so we have to understand what we can do that doesn't change the permeability. For gas shales using hydrofracturing, we're interested in changing permeability in a big way. And hydrofracturing is the technology, along with horizontal drilling, which has opened that up as a viable source of recovering gas from very low permeability shales. But in some respects, it's easier to create permeability that way than in deep geothermal reservoirs, because in deep geothermal reservoirs, you plan to inject cold fluid in an injection well and recover the heated fluid as it grows across the geological heat exchanger from one side to the other. And if you just create permeability that's uncontrolled with fast conduits, then those fast conduits tend to have a positive feedback that makes them more permeable the more cold water you circulate through them. And you end up with thermally short-circuiting conductors across your reservoir. And so controlling the subsurface in terms of the permeability that you produce, and also doing it with minimal seismicity, lots of small earthquakes perhaps instead of one big one, is perhaps the holy grail that we're looking for. And so that's kind of the pretext for this discussion. Induced seismicity has been a big problem in the US for the last decade. You can see the graph on the left-hand side, where rates kick off in the early 2000s, maybe decade and a half ago, 15 years ago. And it's really related to the reinjection of fluids into reservoirs, petroleum reservoirs, in which have a large amount of produced water because they're depleted. But it also has come out as a function of gas shale production, initially due to the reinjection of hydrofracking waters, and more recently also due to hydrofracking itself. In particular in the US, this has raised the profile to change the hazard. So places that once were not seismically hazardous, such as Oklahoma and the northern part of Texas, have become so, mainly due to wastewater injection. And if we had Canada on this, you'd see that also in places that are not very heavily inhabited, in northern BC and northern Alberta, which nonetheless have seismicity attached to them. And so the rates have really gone up. And these events can be quite large. You can see that on the bottom figure in the bottom left, some of these events are approaching magnitude 6 in size. And so they're definitely hazardous. And some of these events, as we will see later, have actually terminated very large projects in deep geothermal energy. It's not a problem that's unique to North America. It has been occurring for, well, a century, I would think, in terms of other parts of the world. India is on this map. Most of the events on India, I think, are due to reservoir impoundments, as in surface reservoir impoundments and changing effective stresses and kicking off events due to that. Many of the ones in the US are due to subsurface reservoirs and the induced and triggered seismicity we've talked about. And by triggered seismicity, I deliberately use a different terminology. By triggered seismicity, we're talking about events which would ultimately happen at some stage in the future, but depending on how primed for failure they are, the extra injection of fluids can result in maybe the strength along that interface and reactivate faults. And those faults can fail either aseismically or seismically. In Oklahoma, as I mentioned, in the central US, most of them have been historically due to recovery of fluids from existing reservoirs and re-injecting the water from those fluids to dispose of them as the brine. But also, especially in Canada and some other places in gas shales in the US, some of these events have been triggered as a result of fluids being injected in massive hydraulic fracturing, which have had the same effect, that the diffusing fluids, pressure diffusing fluids, have traveled distant from the injection point, seeped into faults and reduced effective stresses, mainly by the motion of the pressure wave, and in some cases by changes in total stresses, which is kind of shown on the left-hand side. You can either reduce the strength of the fault by injecting fluids directly in it, or you can increase the stress on the fault by load shedding from the injected area. And so that's important when you look at other sources of these events. A very famous example of which would be in the Netherlands, in the Groningen field, gas field, which has been produced for 30 years, I would guess, perhaps more longer, which is the mainstay of the Netherlands economy in some respects, their energy economy, Royal Dutch Shell. And of course, in that field, you are not injecting fluids, but you're recovering natural gas. And so you're increasing effective stresses as you do that. And so this little diagram on the bottom shows these two different methods of being able to induce failure. The left-hand side is by injecting fluids, you reduce effective stresses, reduce strength, and the same stress that's applied on the fault allows it to fail. And in the other case, you're recovering fluids, you're increasing effective stresses, so the stress on faults increases while the strength remains roughly the same. And that drives failure in the same way by pushing the behavior the other side of the strength curve. So two different mechanisms by which this can occur. And of course, the very famous example of this having happened in a deep geothermal project is in Korea from 2017, I think, right? Which was the Pohang event, which happened after a stimulation had occurred, where a magnitude 5.5 earthquake occurred about 30 kilometers south of the site in Seoul at 4 kilometers depth, which was a fault that was presumably reactivated in some way by the ejection, just from the timing of it. And this ultimately stopped this project, created a review of the processes producing this, and the project is now has not restarted. I doubt if it does. Who knows? It may well do. And the questions are: how do we understand exactly the mechanisms, the propensity that such events would develop? And so we can look at the scaling laws that relate to triggered seismicity, and we'll look at those today. Maybe in overview. I think we might have a broad audience, so I don't want to belabor these things. So we'll talk in overview about these different scalings. And the bottom line is that they scale with relation to the volume of fluid that's injected. They may also scale with rates, but we'll ignore that for now. And we'll look at the idea of injecting fluids into a reservoir, and this little figure kind of explains the mechanisms by which this might occur. So you might inject fluids into a reservoir. The fluids will go out from the borehole to infiltrate an area within that reservoir. And depending on the conditions, we'd be interested to know whether it just reactivates an area within the confines of the pressurized area, or what the conditions are that might allow it to pressurize a certain area, but for the fault to go much further, to propagate beyond the pressurized area, just by the momentum of the strain energy that is released from the system being able to drive it. And so we can look at each of those systems and try and understand exactly what's going on. And what we'd like to know would be, what are the key properties that we need to know? What are the controls, the mechanisms by which it occurs? And what is the scaling that might control it? And we've alluded to 2 potential scalings that might occur. Probably too many equations to really worry about, but the idea here is quite straightforward. The idea is, if you look at the seismic cycle, stress builds up from tectonic forces over time. It reaches a peak, and when it exceeds the strength, an earthquake or a seismic rupture occurs. You drop the stress down to some stress drop magnitude, and then the cycle begins again. And so it matters where on this trajectory you are when you trigger it with the injection of fluid. And so if you think about triggering it when you're almost close to it failing, you can imagine that you don't have to inject very much fluid to be able to move it up an extra 1% to be able to get it to fail. And so we can study that by just looking at Montom's law, where the shear stress change that you get in the strength is given by this shear stress change. Ignore this term for now. This term just allows for the fact that you might be somewhere on this trajectory. You don't have to make it all up at one stage. And we can look at what changes the effective stress. Well, pore pressures do, which we can relate to ejected volumes. Pore pressure relates to ejected volumes. And the shear stress we can relate to the amount of shear strain that is available in this to generate the event. And quite straightforwardly, the shear stress change that you get in this drop is going to be equal to the volume in which the shear strain is released from, and the moment in terms of Newton meters that you release is just given this by this expression. So if you combine these 2 expressions, you end up with a relationship which links the shear modulus to the volume injected to the magnitude of the event through this factor which says how close you are to failure. But the point is that it defines the magnitude of the event as proportional to the volume injected. And so if you plot that, this is Art Magar's very elegant analysis. Our addition is to add this extra term on the front end. And it seems that if you look at a whole bunch of these different events worldwide, then they kind of conform to this relationship being proportional to the shear modulus and the volume injected. If you look at what the pre-existing state of stress is on in your reservoir before this occurs, then you can imagine that these values of the event magnitude is potentially larger as a function of this pre-stress, critical stressing that you have. And of course, this is important because if you look at the Pohang earthquake, the event was much larger, much above this envelope, this threshold envelope. And the question is why? Well, one reason is that it might already be pre-primed in terms of critical stress, ready to kick off with only a relatively small volume of fluid injected. You can do this same analysis for a penny-shaped crack rather than the porous volume which you're injecting. You end up with essentially the same relationship. I don't want to dwell on that. But the question is this idea that you can get an event which is much larger than what you'd predict based on what the pre-existing stress state is that a viable way of doing it? It certainly seems it could be from these observations of Pohang, but there's not much data to suggest that it could be the reason rather than it is the reason. So one way to approach that is in the laboratory to create reactivations of earthquakes. This work is Xian Li, who's now a postdoc at the University of Calgary. And her work was just to be able to generate these earthquakes in the lab, where we had this kind of double direct shear apparatus where a central coupon of rock is driven between clamping coupons. This fault between these, two faults, I guess, one on either side, is fluid infiltrated. And we can raise the fluid pressure within the fault to some magnitude to be able to trigger a reactivation. And then we can use that reactivation to measure the displacement that occurs as a function of time. And of course, we can relate that displacement to the magnitude of the shear stress release which comes out of the system. And so that's really the approach that we're using. So this is the idea, is that you start off with a magnitude of shear stress that's applied on the system. You apply a fluid pore pressure, which you ramp up to different magnitudes. As a function of these different magnitudes, you measure the amount of fault slip that occurs on the fault as it evolves into this unstable behavior. You measure the aperture change as well, because we're interested in things like permeability. And you can convert this fault slip multiplied by the stress that we apply on the system to be able to estimate the amount of cumulative moment magnitude of the event that you get. And so if you do that and you plot these results, you end up with, this is, if you look at the Magar plot, of course, for a laboratory experiment, you'd be way off the left-hand side of this plot because of the injected volumes and moment magnitudes are very small. And so, but if you look at way off the left-hand side of that plot, with the shear stress being 60% of the strength and increasing the pore pressure, this is the Magar plot. And so you can get above this by a couple of orders of magnitudes without too much difference. And so it kind of validates this idea that this relationship could be a viable way to be able to explain the behavior that you see. So that's one way to look at it. So if you plot our data on that plot, then it ends up many orders of magnitudes off to the left. But again, it crosses over this threshold behavior from Magar's relationship, merely relating for the fact that pre-stress might be important. Critically stressed faults don't take very much to set them off. And once they're set off, you reap the full stress drop that was pre-loaded on those systems. So that seems a viable way. But this analysis, our modification of our Magar's analysis, is restricted to the fault only being contained within the pressurized portion of the reservoir. And so if you like, on this little diagram where the pressurized portion is this dark red shaded area, we're restricted to the fault only being that size, where it intersects, or the rupture only being that size. Of course, faults can be much larger. These are typically pre-existing features. And the question is, what happens if the rupture, instead of being contained to within this region, it actually extends beyond this? And so then the idea is that if you have a rupture which has this existing pre-stress, delta tau on it, what is the magnitude of the event that you can develop for that? And that this is a paper by Gallus and Pablo Ampuero in Science Advances from 2017. Very elegant analysis. And in this, I lost my cursor. I don't know where my cursor is. I guess it's back. My screen is. And so if you look at this analysis, you can do this analysis for where the event goes outside the boundary. I don't know why there's back. My pointer's back now. And if you plot this up, the relationship you get out is proportional to volume injected to the power 3 over 2 instead of the power 1 over 1. And so, or 2 over 2, I guess. And so the case that they make is that by having the event go outside this region, you change the scaling. Of course, this 3 over 2 scaling is well recognized as scaling for the magnitude of the event being proportional to 3 over 2 times the length of the fault that fails. And so it's a well-known scaling, not for volume, but for observed fault lengths. And the point is that the data that you have fits this scaling as well as fitting the power 1 scaling as well. So we think we have some data down here where we think that it perhaps doesn't fit the scaling so well. But these are a number of laboratory in situ experiments. These are some laboratory experiments done at the University of Toronto by Paul Young's group. Sebastian Goodfellow, I guess, is the author of those. And they might hint that this could be the relationship that would describe this data. So the question remains as to which scaling is viable. And of course, that's important because once you get to larger events, these would be magnitude 6 and 7 events, it matters whether you're dealing with this 3 over 2 scaling, which seems to give higher magnitudes for a given volume of fluid injected than the Magar events in its normal way. But of course, our analysis allows you to put thresholds which are each basically 1 order of magnitude above that in terms of order of magnitude by looking at the pre-stress. So that's the issue related to scaling. We haven't talked about rates, and we haven't talked about whether there might be limiting values, but you can imagine that different from these scaling analyses that we've talked about, when it's contained within the pressurized reservoir, when the rupture is able to go outside it, then there might also be scalings that relate to the rates of injection. And so if you imagine a geometry where you have a pressurized volume that's pressurizing a fault, but that outside this pressurized volume, there's a permeability that allows leak-off. As this volume or radius pressurized grows, it gets easier for the leak-off to maintain this pressure at some maximum value. So as it initially grows out, because you're injecting, then at some stage, the amount of leak-off that occurs from the periphery of the pressurized zone will equal the amount that's being injected. And so it's at some steady state. And so you can do a very simple analysis with this to be able to look at the scaling of this. And again, you get a similar scaling in terms of the volume injected shear modulus, but this extra term that is defined in terms of what we've called L sub D. And L sub D is kind of a diffusion coefficient. Hydraulic diffusivity, volume injected, the radius of the fault, and the volume injected at constant rate into the center of that fault. And so you look at these, this expression here gives you, if you plot on the same plot as before, it gives you a relationship which follows the original relationship initially, but it caps it off at some magnitude above which it can't go. So the threshold for an LD of 10 to the minus 14 gives you this value up here, but then the magnitude won't change. And of course, the magnitude won't change because the amount of strain energy that you can release from this fault is remaining constant, because it won't fail the material up here, because this is the failure magnitude that has to be exceeded for it to fail. And so you can imagine defining the limits on this in terms of relationship. So, of course, the magnitude of this increases with an increase in the hydraulic diffusivity. Hydraulic diffusivity is proportional to the permeability, the bulk modulus, and the friction coefficient in some respects, no, the permeability, the bulk modulus, and also time in this particular case. This represents kind of a timing related component. So it's not a physical coefficient because it changes as a function of how long you're injecting fluid into the system. So you can imagine that if you put this all together, potentially you have these different scalings, the power 1 scaling, the power 3/2, and caps on each of these, which are related to this reaching a maximum pressure above which you can't go, and therefore limiting the magnitude of the magnitude event that you'd expect. And of course, in terms of the existing database, in terms of these uncontrolled in situ experiments, they kind of fit all of these. They fit our new relationships. They certainly fit the 3/2 scaling. And depending on the permeability that you have in the system, they certainly would be allowed to occur based on the fact that you have a low enough permeability to be able to get a large enough magnitude of pressure developed in the reservoir that's far enough away. So that's kind of a complex of these. I won't spend much time on this, but only to make the point that when we're talking about POHANG, we're talking about isothermal conditions. You're injecting a cold fluid into a hot reservoir. The analyses of the POHANG system ignores that. We assume that it's isothermal everywhere. But the other thing that you can expect to happen within a geothermal reservoir is that if you're injecting fluid, you're creating a pressure change, and you might develop seismicity in the stimulation phase from that. But after a couple of months of injecting, you'd expect that the permeability and stimulation of the reservoir that you're creating has reached some steady state. And so the permeability isn't changing very much. And so if you're injecting constant fluid, the pressure distribution isn't changing very much. But what you'll be doing is you'll be changing the effective stress by removing heat from the reservoir out from the system. And so that removal of heat can create thermal strains, which reduce effective stresses and can give you long-term reduction in strength, which can give you long-term seismicity, not related to any pressure change, because pressures are roughly the same, but due to the fact that temperatures are dropping. And you can do analysis, a very simple analysis, to look at that behavior. And largely what you see as a result of this is you end up with a similar relationship, which is given at the bottom here, but with an extra term that relates to the temperature drop in your reservoir, the thermal expansion coefficient of the reservoir rocks, porosity, and the ratios of the densities and specific heat capacities of the fluids, the rocks themselves. And if you calculate exactly what that term should be, you end up with a similar plot before, but the axes are changed. And so in other words, the volume you inject of cold water to get that behavior is 3 orders of magnitude larger than isothermal behavior. And so it's just shifted by 3 orders of magnitude. But this would be a prediction, if you like, if you get over, don't produce induced or triggered seismicity when you first do your stimulation due to the pressure change, then you might still create seismicity in the long term when the reservoir gets cool enough to be able to reduce the strength far enough that you can then reactivate faults and then create seismicity in those terms. So that's kind of the big picture, if you like, in terms of triggered seismicity and the scalings that I'm kind of excited about, because I think there's some open questions. We don't really know what the scalings are, and they certainly have different ramifications for each of the scaling formats. And it's clearly something we have to figure out to be able to have some confidence in the predictions that we do. The good news, I suppose, is that McGar originally, from 1974, doesn't do a terrible job of predicting this, but it certainly doesn't pick up all the outliers we have. But the other issue that we're interested in relating to these systems is what happens to permeability as a result of this. And of course, in geothermal reservoirs, we want to create permeability. We probably have to create some seismicity to do that, but we like to control it to be less. And so what we'd like to do is that we know that in reactivating very large faults with any real reasonable stress drop, we generate very large magnitude earthquakes. And so what we'd like to do since we know that the magnitude of these induced seismicity events are the order up to 6. So these involve faults which are actually quite large, kilometer size and larger. And so what we'd like to do is be able to avoid that. We don't want to create permeable conduits on these faults. We certainly don't want to create seismicity which is of that magnitude, which will terminate a project. And so we want to find ways to be able to create the same moment release, but maybe through lots of different earthquakes. And so the feedback that we have from these events is in creating permeability. If we're looking at CO2 sequestration, typically reservoirs are transected by very large faults. You get permeation of fluids on those faults. If you reactivate the faults, then you would be worried about the changes in permeability that might give you fugitive emissions that might completely void your reservoir by releasing all the inventory, which counteracts the whole idea. And so we need to understand a little bit about the permeability of faults. The main things that we need to understand is that faults typically comprise a core where all the deformation occurs. Those are large deformations. They might be centimeters, meters, kilometers of deformation. They're typically ground, comminuted material, which has very low permeability. And flanking that core is a damage zone, which typically is just fractured, broken rock, which tends to be almost as strong as the country rock, but the permeability is vastly increased beyond the country rock because it's been damaged by the motions of the fault. The fault core itself will be low permeability, so it acts as a barrier to flow across the fault. It won't conduct fluids along the fault, but certainly the fault damage zone will do that. And so we have to understand something about the architecture when we're thinking about fugitive emissions, because these will not be on the fault core itself, but on the flanking damage zone, which is what we might be interested in. We also know that earthquakes, when they occur in two bifurcated categories, either real earthquakes, the ones that shake your house and knock it down, or slow earthquakes, which occur over much longer durations, maybe months to years, with the same energy release, and as a result of that, are much less damaging. In fact, they can occur without you even realizing that they're there. And so you might think that whether you get an earthquake, which is a regular jarring earthquake, all the deformation and energy release occurs in 90 seconds, has a different outcome, both in terms of energy release rate, damage that results, but you could also imagine that the resulting permeability change would be different in those two cases. And so that's what we might want to look at. And so we've been looking at that for some time. And we need to incorporate into that our ideas of rate-state friction. We use rate-state friction to be able to determine behavior. I won't dwell on these. And you need to have really three conditions to have an earthquake. You need to have strength, which is less than a stress that is higher than the strength. So you need to fail the rock. You have to fail the rock in strain weakening mode. So as you deform it, it has to get weaker, otherwise it will self-arrest. And you also have to have a system where the stiffness of the surrounding system is softer than the fault itself, so that it ejects all the energy into the fault instantaneously as an earthquake, rather than just being ductile deformation. So it's like catastrophic failure in the lab, where you stress a specimen. The specimen is stiff, but the loading frame is soft, and all the energy from the loading frame comes out through the system. And that's defined in terms of this system stiffness K sub C. And we can define it in terms of these terms, which is effective stress, the distance over which failure occurs, and also this parameter B minus A, which is important because when this term A minus B is negative, it means it's strain weakening. When this term is positive, it means it's strain hardening. And so that's the other requirement we have. And so what we can use is this term, this stiffness, to be able to examine the conditions for seismic deformation and seismic permeability change. And the one term which is a function, a strong function of the material properties, is this term A minus B, which defines either strain weakening or strain softening. So we use that to be able to define, potentially, the styles of deformation that occur. And we use that to suggest the styles of permeability change that might occur by suggesting maybe that if you deform brittly, you'll dilate and you'll increase permeability through the fractures you make. And if you deform ductily, strain strengthening, that the permeability change might be a reduction in permeability as you heal things over time. You can do these experiments in the laboratory, but you can also do them in the field laboratory. These were experiments that were exactly like Zian's experiments, which we looked at before in terms of defining the moment magnitude, where in terms of, instead of a sample in the lab, you use a borehole with a packer arranged that is clamped above and below a fault within the borehole, Yves Guglielmi's tool. You pressurize the packed off volume and you measure the shear and normal deformation that occurs across the fracture, just like you would in the laboratory. And so you pump up the fluid pressure by increasing the injection rate. It increases the pressure. As pressure increases, it reactivates the fault, originally elastically. Then it deforms. This is fault opening, shown here, and this is fault slip in a solid line. Initially, there's no seismic energy that occurs with it at all. And at some stage, it begins to generate small earthquakes as a function of the fact that the patch is large enough, maybe, to fail in seismic mode, because this relationship, which defines the critical stiffness, is also a function of the length of the fracture as well as shear stiffness of the rock. So as this fracture gets larger, the rock mass gets softer because it has a larger fracture in it. The system stiffness is softer, and therefore it has a propensity to fail aseismically initially, but as the fault gets, the reactivated patch gets larger, then it can inject that energy through a larger system because it's softer. So we know those behaviors occur within faults at field scale because we see changes in permeability within faults, and we recognize changes in the stiffness of faults by shooting across faults with seismic tomography. We see exactly the same behaviors in the lab where you increase the permeability when you fail it, and it slowly heals over into seismic periods. And you also get changes in the delay times across fractures. Initially, they become soft once it fails, and as it heals, it becomes stiff again. And so you can detect those potentially as precursors, some would say. And so we can do these experiments in labs. We know that rate state friction is a way of looking at second order effects of friction that really honors the behaviors of faults, the second order frictional behaviors of faults, where you get this initial strain or velocity weakening behavior, which makes the initial, the final strength on the fault lower than it began with. So it's velocity weakening. And we can use rate state friction to also relate that frictional behavior to dilation on the fault, which we can then link to changes in permeability. So we use rate state friction to represent the frictional evolution of the faults. We know that that frictional evolution also defines dilational evolution of the fault, and we use that dilational evolution to be able to predict what the changes in permeability. And I'll miss that. We do it in the lab on single sheared samples with fluid pressure and driving flow across them while you shear them. So permeability is measured while you shear them. And typical results would look like this. You measure in the blue dots the magnitudes of fracture permeability as occurs. You provide a reactivation. So you increase the deformation, you potentially increase the permeability. The red dots now are the measurements, and the model of those systems based on rate state friction are the solid black lines you see. So the idea is that we know that rate state friction describes friction and second order friction effects. We know it also predicts dilation on faults and the kind of mechanical deformations that occur. We use that then to translate into predicting permeability, with the idea that we can use this value of the A minus B parameter, stable, non-seismic behavior versus potentially seismic behavior as being a demarcation between different modes of failure. I'm going to skip this as well. We also know that this velocity weakening or velocity strengthening behavior is a function of mineralogy. And so we can look at shales in this particular case, which are silica dominated, run these experiments where we see that the friction increases as a function of shearing, and permeability also net increases as a function of friction for a positive value of this A minus B value, representing shear dilation and velocity weakening behavior. And we can also do it for shales, which are mainly clay minerals, and we get the opposite behavior. Again, we get frictional changes that occur, in this case, an increase in big increase in friction, and a reduction in permeability that occurs. Not a very clear signal, but nonetheless something that's going on to be able to define these behaviors. And so we make the point that understanding something about the style of deformation is important in understanding styles of permeability change that you might get within the reservoir. And so one way to codify this for a whole bunch of laboratory experiments is to look at, on the bottom here, the contents of clay minerals, carbonates, and silica minerals. To use this strain weakening or strain strengthening parameter as a proxy for the mode of failure. So as this value decreases, you're moving towards earthquake behavior. So for the silica rich materials, as you increase the silica content, you tend to have in earthquake modes rather than ductile mode. And both for clay minerals and for carbonates, as you increase the carbonate or clay contents, you tend to get ductile behavior. And the ramification for this in terms of changes in permeability is that for earthquake-prone behaviors, you'd expect that you increase permeability by dilation, by making new fractures, opening fractures. And for cases where you get ductile behavior, you get the converse behavior, where you tend towards getting healing response. So we mentioned before that the controls on these behaviors we think are related to velocity weakening and velocity strengthening. We also made the comment that you need three conditions for an earthquake. It has to fail in velocity weakening behavior, and it also has to be a system where the relative stiffness of the system is lower than the fault itself. The fourth mechanism that's important is that we also have to have it heal. And the idea is, if it doesn't heal, if it develops a low strength once you fail it in an earthquake, then if it stays at that strength, then it will never fail again because it will just deform at that low strength forever. But if it doesn't move anymore, it's static, it will heal and get stronger. And the potential is that it will also seal. So one way to test for that is that you run these shear experiments, but you hold them for a certain period of time, either for 10 seconds or 100 seconds or 1,000 or 10,000 seconds. And then you reactivate it and you measure permeability after you reactivate it. And so this is the behavior that you see. If you measure the behavior after you reactivate it, you see this very characteristic uptick in permeability as you re-shear it. And then you get this power law decay of permeability over the long interseismic period where it heals and seals. And then when you reactivate it again, you get this uptick. You get it quite predictably in a bunch of different samples, both westerly granite and shales. And it follows this behavior, which is actually very similar to what you see in field evidence for this behavior. You have an earthquake, the permeability goes up, interseismic periods, it goes down. And so you can try and characterize this in terms of a simple model for permeability. Here's one that tries to fit it to this power law change in the aperture as a function of time, because we know the mechanism by which it heals is by, you can relate to power law creep, if you like, and we can tie that behavior together. Where perhaps the main take-home message is that if you take all of these results for different hold periods, so maybe for 10 seconds, 100 seconds, 1,000 seconds, 10,000 seconds, etc., and you shift them all so that they're all laterally removed, so the time of reactivation is given as times T0 here, then for the shortest hold periods, you see that the fault compacts and the permeability decreases. But for the longest period, the fault has healed, has become stronger, and as you reactivate it, it dilates and it produces the greatest permeability increase. And so there's a correlation, not a very clean correlation, but one that talks about the longer the interseismic period, the longer you wait for the next event, the stronger the fault becomes and the larger the magnitude of the permeability increase that occurs. But of course, that ultimately is staunched by this steady state reduction. So that's fine. So I'm roughly on time. I didn't know the conclusions were coming up straight away, but you might be happy that they're here there. So I think what I tried to illustrate is that seismicity is a problem in all of these systems that we deal with. It can be a project-terminating hazard, which can shut these projects down. It certainly has done in deep geothermal projects, Basel in Switzerland, Pohang in South Korea. But it occurs ubiquitously in any of these systems where we inject or recover fluids. We can scale the magnitudes of the events that we get according to the volume that's introduced into the subsurface. It's not quite clear exactly what that scaling should be. It changes based on your assumptions as to how far the rupture control can go beyond the pressurized volume. It also changes as a function of your assumptions on rate effects and drainage that might occur in the periphery of the fluid. So we can end up with a variety of scalings depending on the system we have, but we have a pretty good idea of the general behavior we get. And the data for field projects actually is kind of unequivocal. It doesn't really point to any of these three scalings because it seems as if it can satisfy all three of them at that scale. So the potential one is not absolutely clear. If we're interested in events that are seismic, then that is the mechanism also by which you can generate permeability in reservoirs, if you want to do that, as in gas shale reservoirs and deep geothermal reservoirs. And also that knowledge of what not to do to create permeability is useful if you don't want to create permeability in cap rocks. And so making permeability or avoiding permeability, this idea of seismic versus aseismic deformation is quite important. If we look at the ability to generate or avoid making permeability, we can relate it to this idea of stiffness, critical stiffness, which is a function of the patch dimension, the size of the fault. It's a function of the brittleness or ductileness of the materials making up the fault. And it depends on whether we're looking at the fault core itself or the damage zone which flanks the fault core, which would be fractures, which would be reactivated. We said something about the propensity to develop earthquakes. There's three parameters, but there's actually a fourth. And that fourth parameter is that healing and making a strength stronger and sealing, making a strength less permeable, is an intrinsic part of the seismic cycle. And if we want to understand the seismic cycle, we need to understand that effect as well. If we have longer interseismic periods, then the healing is larger, the strength of the fault increases more, and then the reactivation of that tends to have a bigger effect on changing permeability. A larger increase after longer healing and stronger strength gain. And so the general point, I think, of what we talked about today is that, as you look at the climate crisis as it is, base load power seems to be still required in our energy transmission system, and replacing the large-scale use of coal, petroleum, and transition fuels to natural gas is actually facilitated by all of these deep subsurface reservoir systems. And it seems that we might be on the stage of a renaissance in some of these in terms of actually implementing these potentially at large scale. And if we do that, then clearly the things we talked about today are things that we want to be mindful of in terms of being able to avoid and to be able to control in some way exactly what's going on in the subsurface. So I'll leave it at that, and I'll be happy to take questions as you so wish. Thank you very much. it's always a bit soulless when you talk these because you have no reaction from any audience you have. I will try and turn my pen back to an arrow. I think I need to do that to be able to get the chat. The chat has been closed.
Yeah.
Oh,
Thank you.
no
Thank you.
questions.
Thank you, Professor. Thank you, Professor Elsworth. I think it was a great talk. So we have, I think, one from the Q&A in the Q&A box here. I think we'll also get more as the as it goes on. So the question that we have right now is that can we use the micro seismic data for reservoir permeability mapping?
Yes, yeah, I think you can. And of course, it's a very useful technique for that. In fact, the other thing that I didn't talk about today is that since we've tried to make this connection between deformation on faults and moment, of course, seismic moment is something that you measure in microseismic, in the recording of microseismic events. And so there's no reason why you can't, and we've actually attempted to do this, is to use the information that you have for linking moment magnitudes of events with the deformation that fault reactivation would go through. And if you think about, well, it's actually linked. I guess I can't move it back. Can I move back? No, I didn't want to go there. If you use these models, and I guess the critical model is this one at the bottom of the page here. If you can link the change in permeability. So first of all, to answer your question, yes, you can define exactly where these events are, and therefore you can see exactly for seismic, the induced changes in reactivation. You can pick up those locations and you can track the location of big hydrofracks, and you can track the location of off main hydrofracks reactivations if you have sufficient resolution of the events themselves. But also what you can potentially do, which I think is kind of an exciting area, is that you can try and link the magnitudes of those events to try and predict exactly what the spatial distribution of permeability changes is within the reservoir. And to do that, I think you can use a similar idea to what we've talked about here. We've tried doing it. So the idea is that if you can link a change in permeability to a change in aperture, if you can somehow link the change in aperture that you get to the magnitude of the event that you're recording, then you have an ability to directly predict a spatial distribution of change in permeability with location. And so you certainly can do that. And there's a paper in Geothermics, I think in 2016 by Yifang and myself and Trenton Cludis. You should be able to find it if you're looking for it, that tries to do exactly that. Take the data from the Newbury EGS project, their stimulation, take the individual events, use moment tensor solutions for those events to define the orientations of the fractures, use the magnitudes of the catalog events to be able to define the magnitudes of the events, use those magnitudes to define both the size of the fault and the shear offset, use that shear offset correlated with an assumed fractal roughness of these fractures to calculate the dilation, and use that dilation to exactly calculate exactly what the value of the permeability is. So that's the workflow that we use there. So I refer you to that geothermics paper. So should I be reading these myself?
Sure.
Can you please comment in case if you encounter highly porous reservoir, what are the requirements for instability and seismic effects? Well, highly porous reservoirs, I guess, would give you the ability that you don't increase pressure so much because the flow will be much faster. And so I think that's kind of embodied in this idea here, is that if you had a highly porous reservoir, one, fluids would flow for much larger. So the pressure you generate is a function of the injection rate and the permeability of the reservoir. High injection rates and low permeabilities give you maximum pressures, and high permeabilities and low injection rates give you the converse. And so the ability to, or the likelihood to generate instability in a highly permeable reservoir with a low injection rate are smallest. means that you probably increase the injection rate and then the pressures increase. But I think you can use these characterizations uniformly, because these characterizations are, especially for the geometry that we talked about, that if you get large enough, a porous reservoir, high porosity reservoir, would mean that this diameter in this particular case, or the radius r, would actually be very large for a very small pressure gain. And so if that's the case, then the kind of behavior you'd expect to be would be you'd be at a value of this, which would be linked to being relatively low. So a low value of this value would be, these are increasing values, they're very small, but they increase as you go down. So it's an inverse relationship. So the higher the value of permeability you have in the reservoir, the larger you'd be going downwards on this plot. So the magnitude of the event that you expect to get after you reach some kind of stable equilibrium would be lower. So, highly porous rocks means you pressurize a bigger volume, but the magnitudes of the pressure change would be smaller, and the likelihood of generating an event would be smaller. I think you can use these kinds of characterizations universally. So clearly, the impact of permeability is important in these. It's not identified in this one, but I think it's identified in the previous one. It's also a function of the volume that you're introducing. So if you have, if you reduce the volume that you introduce, you also increase the value of LD, in addition to increasing the permeability. So both of those effects on it. So hopefully that's answered your question. Let me know if it has not.
So we have one more question here in the Q&A box, and they're asking, what are the limitations of the rate state friction theory? And is this theory applicable for modeling field scale reservoirs to predict CO2 injection induced seismicity?
Yeah, well, I mean, rate state friction behavior has been used as a very straightforward way, much less complex, for instance, than if you're working in a geotech program where you have lots of complex constitutive laws to describe behavior. Usually it's a very simple experiment, shearing of a sample. Usually experiments are done not in terms of stress control, but in terms of strain rate control, constant velocity perturbation. And it gives a very simple output, which gives you these second order friction effects that pick up this very definitive behavior of the fact that whether friction strength goes up or down as a function of deflation. So whether it's velocity weakening or velocity strength. So it is broadly used in the earthquake physics community, just because it really accommodates most of the observations of field behaviors. Certainly, it also accommodates behavior that represents, as we mentioned in the presentation, it accommodates not only the deformation behavior that you see, but it also accommodates, for instance, dilation for a particular figure, like that in this figure. And so not only does it pick up the changes in deformation that occur in terms of strength loss as a function of shear, as you do these experiments by perturbing the strength, but it also picks up dilation, which goes to a steady background dilation as you get steady state shearing. This is not without velocity, this is a steady state shearing velocity occurring with displacement. So it picks up most of those influences. It's usually applied on a plane to represent plane, not distributed deformation that occurs in a reservoir within a plane. And it's widely used to represent, it really is just a way of saying that it picks up this velocity weakening behavior. So there's nothing special about using rate state friction. It's just a very simple constitutive model that picks up this second order frictional behavior that seems to be useful in representing the physics of earthquakes, also can represent the dilation that occurs. And for our purposes, we can use that dilation that we see, that we measure in these experiments, to represent reasonably, with reasonable fidelity the changes in permeability that we see in this tool. So it's just a very convenient system to use. So the question was, is it used in the field? Yes, it is. Does it work in the field? Yes, it does. It seems to honor observations quite well. And why do you use it? Well, we use it because it honors observations and allows us to link deformations to dilation to permeability, which is useful for us in being able to represent the system throughout the entire earthquake cycle. Creating the aseismic or seismic event is explained by rate state friction. After the healing behavior in the interseismic period is also represented by rate state friction. And since it represents those behaviors in both of those times, in other words, throughout the full clock, before failure, during failure, and in the interseismic period after failure, since it allows us to be able to link deformations to dilation to permeability, it just ends up being a useful tool that transcends both field and measurement in the laboratory. So yeah, I see these things online now. Are there any experimental results available to study wave propagation due to CO2 injection induced seismicity? To use these data for wave field simulations. I think certainly there are not in our lab. I know that one of my colleagues, Tiyuan Zhu, has been interested in looking at Q measurements and wave speed measurements, so attenuation and changes in velocity as a function of saturation of different phases within reservoirs, including those within CO2 sequestration sites. So, and trying to look at different saturations to understand what those magnitudes would be, and also in terms of applying it to the Cranfield site in Mississippi and southeast US. So the name is Tiyuan, Tiyuan, last name ZHU, and he's a Penn State. And so you might want to look at his work. I seem to remember a paper in the PNAS, the Proceedings of the National Academy of Sciences, that talked about that very problem. So if you want to email me, I could probably find it and email it back to you. But our work hasn't done that. But I think that's an interesting question to understand whether you can, image a reservoir to predict saturations. The idea, of course, would be to test for the inventory of CO2 that you have to make sure that you haven't lost any, and also to be able to prospect to see what the pressure distribution might be, to see if there are zones where you might be wondering about triggering seismicity, and therefore do something about your injection schedules.
Thank you, Professor Elsworth. Abhijit, do you want to ask? You had several questions.
Yeah, sure. Yeah, Professor Elsworth, this is the talk which I have been waiting for some months, okay? Because, yeah, this is very interesting talk and thought-provoking. And I have some question. I will have many more questions once I go to listen your talk, the recorded talk once again. Probably I'll contact you. So the immediate some questions which I want to ask you now. So you have been, I mean, it's very nice that you got a very nice theoretical scaling among the injected fluid and the magnitude of earthquake for different conditions, the constrained, unconstrained, and other one injection rate limited. So my question, first question is that the unconstrained rupture, then runaway rupture or uncontrolled rupture, do you mean they're same, or I mean you use all three words?
Yeah, I see the question now on the chat. It might be your question.
Yeah.
High injection volumes, they seem to merge into each other. So my explanation of that is, I think I understand what you're talking about. So the physical mechanism, what's going on is that, you're talking about this behavior that initially you start off on this curve and then you reach some threshold, and this is now the new threshold. I think the reason for this is that, so initially as you start pumping into this very high permeability reservoir, then as you inject, then you'd expect if the reservoir is very high permeability, then it will fill up the reservoir just like filling up a bucket. It will be uniform pressure, and the uniform pressure will rise. As the uniform pressure rises, it will try and leak out into the lower permeability host around that reservoir, say a low permeability part of the fault. And only at some magnitude of pressure, for constant injection rate, will the leak off out of the side be equal to the amount that's coming in. So as you rise up here, the amount of pressure will be rising to get to this maximum threshold. So I interpret that as being the case where the pressure, whoops, going in the wrong direction. But you're filling up the bucket and you're heading along this trajectory here. The pressure is rising within the bucket until you get to the peak magnitude. And as soon as you get to the peak magnitude where the magnitude of the injected fluid is equal to the amount that's removing from the periphery of the fault, this is that point exactly there. Now you keep on injecting. The pressure doesn't go up anymore because it leaks out of the side of the fault at exactly the same rate you're adding it. So the pressure has to stay constant. So you're increasing the injected volume, but you're not making any change in the pressure profile within your fault. And so the moment that you release, if you fail it, can't change. And so that's the physical explanation, I think, of what's going on. You've reached the peak pressure in the reservoir at this point here, and now it's leaking out of the sides just as quickly as you're adding it. So the magnitude is always going to be the same. If it happens to be a lower permeability exterior material that it's leaking into, then the pressure will keep on rising until you get to this point here, and then it will reach a steady state. And so the event you get will be larger because the pressure within the reservoir will be larger itself. So I think that's the explanation of the physical explanation of really what's going on in this particular system.
Yeah, okay. Yeah, now my other question is that runaway fracture, is it related to the creation of new fracture due to hydrofracking?
Yes.
Okay.
So can you ask the question again? I heard
the unconstrained rupture or runaway rupture are the outcome, or I mean, are the consequences of new creation of new fracture due to hydrofracking?
Yes, well, certainly this, it's kind of like, well, it's a bit like hydrofracking, but these ruptures that we were talking about for earthquakes are not in mode 1, they're either in mode 2 or mode 3. And so the shear ruptures, which defines the moment, but you can get similar behavior. Really what it's saying is that if you overstress the fracture, then you can fail it, and that rupture can be either constrained to the periphery of that pre-existing fracture, or it can extend beyond it in shear. So this, the shear behavior is, I guess, in mode 3 or in mode 2, either one you can look at, that it goes beyond the existing pressurized contour. I think you get the same happening in hydraulic fracturing. In this particular, in hydraulic fracturing, the strain energy that you're applying is in the fluid that's compressed within the existing contour of the hydraulic fracture. It's kind of aligned parallel and perpendicular to the minimum principal stress. And so it would not so much rupture in shear, but you could rupture it, I guess, beyond the rupture, as you do in a hydraulic fracture, just due to the strain energy. In fact, you know, lots of people believe that this lag that you have at the tip of the fracture is the space where the fracture develops before the time for the fluid to be able to infiltrate into that, and you get a gas-filled zone, which is at the vapor pressure of the fluid ahead of the rupture. So that would be kind of the analog, I think, to this unconstrained rupture, the 3/2 scaling versus the constrained rupture.
Okay.
So I don't know if I answered your question or not.
Okay. So between this unconstrained and constrained rupturing, which is more common in the reality, causing more seismicity?
Good question. I don't think we know. I think we know the size of the events that occur. I think we can map the faults that fail and the extent of the failure. but I don't think we have a good constraint on the size of the stressed zone. So I think we understand, if I go back to a picture of this, probably from these existing earthquakes, we certainly know the magnitudes of these ruptures as they occur, but we don't know whether the initial pressurization was up to the lips of these or just a very small part of the interior of these. So I'd say the major unknown we have, except for the few laboratory data we have here and our work that we have here, are not defined in terms of the pressure distribution. So we know the outcome of the fault rupture, how big it is, but we don't know what the red pressurized region is very well. So I'll take a pass on answering that, to say we don't know.
Okay. And regarding the permeability change with time or with displacement or sleep, it is very interesting to see that I was earlier thinking that permeability would increase over time, but your result shows permeability decreases with time. So is it the case that when the slip happens, the surface becomes smooth, the interface between fracture and the rock matrix becomes smooth, and the aperture decreases?
Yeah, I think the mechanism is that when you fail it in a seismic event, you get brittle failure, you get some kind of dilation occurring, and the permeability goes up. These are field results actually from the San Andreas Fault, or from earthquakes close to the San Andreas Fault. The vertical dashed lines are far field earthquakes. The dotted lines are measurements of permeability from earth tides. And so these are two different wells measuring permeability. So permeability goes up when it fails, and it goes down over time up till a new event, which it goes up and down, etc. So you see the kinds of behaviors that we see in the laboratory, also in situ, in natural systems. And so what we think is going on here is that when you reactivate it, it dilates, permeability increases. And then over the longer term, it heals. These are exactly the same data we looked at before. And so what we think is the mechanism is that it's creep on the asperities. So the fracture is held open by, it has some bridging asperities that prop it open. And that because the stresses on those are relatively high, that they preferentially dissolve because the chemical potential of those is increased, and they preferentially dissolve relative to other material on the fracture face. And if that bridging asperity is dissolved, then the fracture gets closer together, and if it's closer together, its permeability will be lower. And so that's one of the explanations. Other people, including us, have explained also this drop in permeability as due to the mobilization of fines which clog the fracture. So that's also a mechanism that's used to explain it as well.
So some kind of chemical reaction involved, dissolution involves in this process.
Well, transport of fines would be not necessarily involving chemical reaction. It could just be mechanical straining and filtration. Some of them could also be chemical changes as well. You make new surface area, you increase the potential reactivity, and therefore reaction rates are increased, and therefore you get some reaction occurring quickly once the fresh surface has been made. So lots of things can potentially explain it. Definitively identifying exactly what it is not so easy, but certainly you can advance a number of ideas of what it might be.
Okay, thank you so much. Thank you so much.
Good. All right, great. All right, are we finished?
I think Ramesh has some question. I think you see.
Okay, are they posted somewhere, or are they
in the chat box? I think Ramesh. I think.
Yeah. So. Yeah, the question is like high injection volume, the constrained and unconstrained, the moment sort of merges. Any comment on that? Just a quick question.
I think I tried to address it before, but I'll do it again. The idea is that if I understand your question right, is that but they're this kind of cutoff. So I think the idea is if I do it here, is that you're merely using threshold for these behaviors is given by this red line if you have leak off. And the idea is that this initial one-to-one slope is the time where you are filling the bucket up. It starts off with the zero pressure within the bucket, and it fills up this permeable fault all the way to its edges, but at a very low level. So as you keep on injecting fluid at some fluid injection rate, this surface slowly increases up to some magnitude. It has a low permeability exterior and a very high permeability fault. And so this low permeability exterior controls the leak-off rate. When it's a very low pressure, the leak-off amount is very small because the leak-off is going to be proportional to the pressure multiplied through by the permeability and some geometric factors. The pressure is very low, and so the rate is very low, and it's probably less than the injection rate that's pumping into this box. At some state, this pressure will increase because it's not escaping to the outside. And at some state, the amount of fluid which is being driven to the outside by the pressure drop delta P multiplied by the permeability multiplied by some geometric function of this radius will be exactly equal to the amount that's being injected. And so this pressure will not change because the amount that's leaking out to the side is the same as what's going up. So the pressure can't change. And so that's the step when you exactly find yourself at this point here. So the pressure's been rising. So the moment's been rising because the pressure has been increasing all the time. You can then generate a larger event. But now the pressure profile is looking exactly the same. It's not changing anymore. If you look at this when it reaches this and you look at it 2 years later, the pressure profile will look exactly the same because it's leaking out. And so since that's the case, you wouldn't expect the moment magnitude to change at all. And so as long as you keep on injecting fluid, so we're going along in time here, it would be in log time, I guess, because this is a log scale. As you keep on injecting, you'll just go along this trajectory here and nothing else will change. So I think that's the mechanism by which this behavior occurs. Before it reaches its peak, it behaves just as any other reservoir. Once it reaches its peak, then it can't create an event which is any larger than before. Does that answer the question?
Yeah, thank you. That's all.
All right.
I
don't see any more chat questions. Are there any? And
are there any further questions from either the audience or the panelists?
Oh, we have a panel, do we?
Okay, looks like there are no further questions. So in that case, well, thank you very much once again, Professor Elsworth, for taking the time for giving a webinar at our series. It was a pleasure, and yeah, we look forward to interacting with you and staying in touch.
Yeah, great. Thanks for spending time with me. Thanks for giving up your dinner hour. Maybe you ate before, or maybe you ate now. But thanks for. I know it's a less convenient time potentially for you than it is for me, middle of the day. So thanks very much. Nice to have met you all, and we might be talking again, I guess, sometime in September. So.
Yeah.
Thank you. Thanks.
Thank you. Yeah. Bye now.
Great.
Bye.
Take care.
Thank you.
Bye-bye.
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 Take care.
I don't know if I can